Let's see the design of crankshaft subjected to maximum twisting moment. In the last video, we have seen the crankshaft which is subjected to maximum bending moment. So now here is maximum twisting moment. The maximum bending moment condition is the condition when the force acting on the piston is maximum. The force acting on the piston will be maximum when the gas pressure on the piston will be maximum. That means when the gas pressure will be equal to Pmax, the force acting on the piston will be maximum one, and at that stage the crankshaft component will be subjected to maximum bending moment. But as the piston will start moving from the dead center, the force P will be reduced. Now piston is moving downward. So here in the green curve is crank, here the different color. So here with crank is making certain angle, piston is coming down, force on the piston is reduced, force on the piston is again reduced, and the crank is making certain angle, and at the particular angle of the crank, so let that angle equal to theta degree. Force acting on the connecting rod is let Q, and angle made by the connecting rod with the center line is phi. Now the Q force is divided into two components. One is Ft, another one is Fr. Ft is the tangential component of force, that is force acting on the connecting rod, and Fr is the radial component of the force. Tangential component is making the crank to rotate, and this radial component is directed toward the center of rotation. Herewith the tangential component is always perpendicular with the crank. So the angle between the tangential component Ft and crank will be 90 degree. Looking at the trigonometry of the figure, here theta is the crank angle. So these two angles are equal because angles are opposite. So this angle is also theta. Then this angle is phi. So here is also equal and opposite angle phi. So these two angles are equal and opposite. Then these two angles are equal, phi. So this total angle will be equal to theta plus phi. Then as this Ft is perpendicular to the crank, here angle is 90 degree. So this angle means angle between the direction of the connecting rod and the angle which is in the angle between the direction in which the Q force is acting and its tangential component is 90 minus theta plus phi. So this angle is 90 minus theta plus phi. So let's say how the derivation for finding how much is tangential and radial component of the crank pin forces. The twisting moment on the crankshaft will be maximum when the tangential force is maximum. But when the tangential force Ft will be maximum. Here in the petrol engine, the tangential force will be maximum when the crank angle is between 25 to 35 degree, and in diesel engine the tangential force will be maximum when the crank angle is 30 to 40 degree. Herewith, let's find the angle phi. So let's imagine that there will be maximum twisting moment acting at the crank pin when the crank angle theta is 36 degree, means angle is between 30 to 40 degree. So let this angle is 36 degree. Now let's find the angle phi. Looking at the trigonometry of the figure, sin phi will be equal to LP, that is the perpendicular length, divided by the length of connecting rod L. Sin theta will be equal to LP by R. R is the crank radius. Therefore, LP equal to L sin phi equal to R sin theta. Therefore, sin theta divided by sin phi equal to L by R. Therefore, sin phi equal to sin theta divided by L by R. Substituting the value of theta equal to 36 degree and the value of L equal to 300 millimeter, that is length of connecting rod. R is the length of crank is 62.5 millimeter. So this L by R equal to 4.8. Substituting the value, phi is the angle of connecting rod with the central line is 7.03 degree. Now, as I just told, that gas pressure is maximum when the piston will be at the dead center. Of course, it will be at the TDC. But the gas pressure will reduce as the piston will move downward. Let at angle theta equal to 36 degree, let the gas pressure is 40% of maximum explosion pressure. I mean, when we are considering that at angle, crank angle 36 degree, there is maximum twisting moment. So let the gas pressure at that condition is 40% of the maximum explosion pressure. So 40% of maximum explosion pressure we have already taken. It is 52.5 kg per centimeter square. So 40% of 52.5 kg per centimeter square, it is 21 kg per centimeter square. Therefore, substituting this value, the pressure acting on, the force acting on the piston when there is maximum twisting moment acting at the crank pin, so that force is given by F dash equal to 5 by 4 into d square into P. So P is gas explosion pressure when crank angle will be equal to theta degree, and when there is condition that there is maximum twisting moment acting on the crankshaft. So it is here 21. Substituting the value, pi by 4, 9.9 centimeter is the piston diameter. Substituting the value of F dash, that is the force acting on the piston at the condition of maximum twisting moment, is 1617 kgf. Now let's find cos 90 minus theta plus phi. So herewith this angle, that is the angle made by the tangential component with force Q, is 90 minus theta plus phi. So cos of this angle, cos 90 minus theta plus phi, is equal to Ft divided by Q. This one is the adjacent side. So cos 90 minus theta plus phi will be sin theta plus phi. So sin theta plus phi equal to Ft by Q. Therefore Ft equal to Q sin theta plus phi. So tangential component of the force which is acting at the crank pin is Ft equal to Q sin theta plus phi. Let's find the radial component. Now sin 90 minus theta plus phi, that is equal to, this is here Fr divided by hypotenuse Q. So sin 90 minus theta plus phi, that will be equal to cos theta plus phi, that is equal to Fr by Q. Therefore Fr equal to Q cos theta plus phi. Hence tangential component, that is Ft equal to Q sin theta plus phi, and radial component Fr equal to Q cos theta plus phi. Cos phi equal to force F dash by Q. Therefore Q equal to F dash divided by cos phi. Substituting the value, F dash is 1617, which we have just calculated. Phi is 7.003. Therefore Q force which is acting on the connecting rod is 1629.25 kgf. So this force has two components, Ft and Fr. So here is the force, this has two components, Ft and Fr. These components are making 90 degree with each other. So the tangential component means Ft equal to Q into sin theta plus phi. Substituting the value, tangential component is 1111.77 kgf. Radial component is Q cos theta plus phi. Substituting value, it is 1190.97 kgf. So here are the tangential component and the radial component of force Q. Now looking at this figure, this Ft is the tangential component of force Q. Q force is here. So this has two components, tangential, radial. This component are making 90 degree. Tangential component is making the crankshaft to rotate it is tangential component. Fr is Fr is the radial component which is directed toward the center. Now this tangential component is balanced by two components which are acting at the journal, that is ht1 and ht2. So they are acting in the reverse direction of ft. So they are directed here, ft is directed in the opposite sense, and this fr is balanced by two components, this one hr1 and hr2. So this fr and hr1 and hr2, hr1 and hr2 are in the same direction, which is in the opposite sense. Let's design the crank pin. Crank pin is subjected to combined effect of bending moment and twisting moment. Bending moment is caused by force, that is reaction hr1. Bending moment we can find out by the multiplication of reaction hr1 and distance a. So this a equal to f by 2. F is the distance between two journals. A equal to f by 2. Bending moment acting at the crank pin will be hr1 into a, and the twisting moment acting at the crank will be equal to ht1, this is the ht1 multiplied by the radius r. The crank pin is subjected to the bending moment and the twisting moment. Okay, so the combined effect of bending moment and the twisting moment is the equivalent twisting moment. So it is given by square root of mb square plus mt square. Mb is bending moment, mt is the twisting moment. So mb is calculated as 595.49. So here is coming on the back slide. This st1 equal to st2, that is equal to fd, that is equal to ft by 2, and ft is 1111, that is 1111.77 by 2. It's calculated as 555.89, and hr1 equal to hr2 equal to fr by 2 is 1190.97 by 2. It is 595.49 kgf. So substituting these values here, this is 595.49, 595.49 into the value of A is 10 centimeter. So it is 554.9 kg centimeter, and the twisting moment is ht1 into r. You can take ht2, and for bending moment you can take hr2 also. Okay, perpendicular distance will be same. Here you can take the value of h2 also, ht2 also. ht1 and ht2 both are same. So this ht1 is 555.89 into r is 6.25 centimeter. So it is 3474.31 kg centimeter. Substituting value of bending moment and twisting moment, square of this. Equivalent twisting moment is 6894.32. Of course, this in kg centimeter. Then this MTE, equivalent twisting moment, equal to pi by 16. This is This one is the generalized equation for finding the bending moment. So here is equivalent. So this is the generalized equation for finding the twisting moment. So here this is equivalent twisting moment. This pi by 16, this is the diameter of crank. This is the allowable shear stress. Substituting the value of MTE, pi and Fs, the diameter of crank pin is 4.646, that is 4.7 centimeter, that is 47 millimeter. But we have already calculated diameter of crank pin in the previous section. You can see it is 65 millimeter. So here it is safe. Then let's see the design of flywheel shaft. So looking at the flywheel is like this. It is not supported. It is supported at one end only. This is hanging type of flywheel. So we can find out the bending moment for this type of flywheel as weight of the flywheel into the distance from support. So here it will be W into G. G is the distance, W is weight of flywheel. Let's take the weight of flywheel equal to 5 kg. This is 5. Let the distance is 20.5. This is considered here. So bending moment will be 102.5 kg centimeter. Twisting moment acting on the flywheel will be force which is tending to, the force which is causing the flywheel shaft to twist is Ft. Ft is the component of force Q which is acting tangentially at the crank. Okay, so same force Ft into R is the crank radius. So this twisting moment is calculated as 6948.56 kg centimeter. Similarly, finding the equivalent twisting moment, substituting value of bending moment and twisting moment, the equivalent twisting moment is 6949.32 kg centimeter. Again, the twisting moment formula, ME equal to pi by 16 diameter of flywheel shaft cube into factor of set. This one is the allowable shear stress is Fs. Substituting the value, we can find out how much is the value of. Now let's see the design of flywheel shaft. Flywheel is of hanging type here. So it is not supported at both ends. It is supported at only one journal. So the bending moment acting on the flywheel will be equal to weight of the flywheel into the distance of flywheel from support. Weight of flywheel is let 5 kg, distance is let 20.5 centimeter. So bending moment will be 102.5 kg centimeter. Here the twisting moment acting on the flywheel shaft will be calculated by Ft into R. So what is Ft? Ft is the tangential component of force Q. Q is the force acting on the connecting rod. So this tangential component is the component of force Q which is causing the crankshaft to rotate. So that Ft into crank radius, So this MT is 6948.56 kg centimeter. Substituting the value of MB and MT, bending moment and twisting moment, this is equivalent twisting moment using same formula. Equivalent twisting moment is 6949.32 kg centimeter. Then the General's formula for equivalent twisting moment or for the twisting moment only, it is pi by 16 diameter of flywheel shaft cube into allowable stress, this shear stress. Substituting the value of ME equal to 6949, which is calculated here 6949.32, and substituting the value of diameter of flywheel shaft as 1.85 centimeter, we can find out how much is induced shear stress in the flywheel shaft. This induced shear stress in the flywheel shaft is calculated as 5589.81 kg per centimeter square, which is higher than the safe limit or the allowable value of shear stress. Allowable value of shear stress in the flywheel shaft is 380 to 420 kg per centimeter square. So ये flywheel shaft में जो induced shear stress हो रहा है, अगर हम flywheel shaft का diameter 1.85 सेंटीमीटर अगर कंसिडर करते हैं जो हमने प्रीवियसली डिज़ाइन किया, तो इसमें इंड्यूस्ड जो वैल्यू है वो बहुत ज़्यादा है, बहुत ज़्यादा आ रही है। और ये डायमीटर फ्लाईव्हील शाफ्ट का ये बहुत ही छोटा आ रहा है 1.85 सेंटीमीटर। फाइंड आउट द diameter of flywheel shaft by substituting the value of safe limit of shear stress as 420. If we substitute the value of Fs as 420 and equivalent twisting moment as we calculated 6949.32, diameter of flywheel shaft is calculated as 44 millimeter. So it is 43.8 millimeter. So let's take 44 millimeter. So diameter of flywheel shaft will be 44. Now let's design the journal. Here are two journals or bearings. One is left hand, another one is right hand. So let's focus on the right hand bearing. Here is the right hand bearing. Okay, this one. So let's focus. So total force acting on the crank pin is F. F is the maximum force when the piston is at dead center. This is calculated using value of gas pressure as maximum explosion pressure. This is F. F is balanced by the reactions at journals, that is H1 and H2. So this H1 equal to H2 equal to F by 2. One reaction. The reaction at journal due to weight of flywheel will be equal to weight of flywheel itself. So total reaction at right hand journal will be equal to H2 plus W. And this journal is considered subjected to bearing loading. So the projected area will be equal to length into, so projected area will be equal to length of journal into diameter of journal. And this is the bearing pressure, that is the allowable bearing pressure. So substituting the values here, the diameter of journal will be reaction at bearing is 2025.5 divided by length of journal is 8.5 centimeters, already calculated previously, and this PB is bearing pressure. Let the value of PB is 50 to 85 kg per centimeter square. Substituting these values, diameter of journal is 4.76 centimeters. So that is equal to approximately 50 millimeters. So this is about design of journal. So these two references are used for this topic. Thank you very much for listening.